Welcome to G Fun Facts Online. Today, we are going to dismantle a very common misconception about our planetary neighbor. When we look at Mars through a telescope or browse images from rovers, we are often conditioned to see a static world. We see a rusted, desolate antique frozen in time, a place where history is written solely in the violent punctuation of ancient impact craters and the silent towering of volcanoes that haven't erupted in millions of years. This view, however, is a deception. Mars is not a dead statue. It is a world of rhythm and flow, a planet that breathes on geological timescales. Nowhere is this dynamic history more vividly etched than in the haunting, scarred landscapes of a region called Coloe Fossae. Located along the precipitous boundary between the planet's rugged southern highlands and its smooth northern lowlands, Coloe Fossae is not merely a geological curiosity. It is a frozen archive. It is a place where the planetary crust was first torn open by tectonic claws, only to be subsequently filled, sculpted, and smoothed by the slow, grinding passage of ancient ice. To trace the scars of Coloe Fossae is to read the diary of Martian climate change, a saga of wobbling axes, wandering glaciers, and a water cycle that has shaped the alien surface in ways that eerily mirror, and yet dramatically differ from, our own Earth. In this episode, we are going deep into the trenches of Coloe Fossae to unravel the mysteries of its formation, the physics of the ice ages that transformed it, and the tantalizing promise it holds for the future of human exploration. To understand the glaciers that once flowed here, we must first understand the vessel that held them. Coloe Fossae is situated in the Isthmianus-Lacus quadrangle, a region defined by one of the most profound and mysterious features on the entire planet, the crustal dichotomy. Mars is essentially a tale of two planets stitched together. The southern hemisphere is a battering ram of ancient, heavily cratered crust, standing kilometers higher than the north. The northern hemisphere, by contrast, is a smooth, vast basin, likely the scar of a cataclysmic impact that occurred very early in the solar system's history. The boundary between these two worlds is not a clean line. It is a shattered, chaotic fracture zone, and this is the domain of what geologists call the fretted terrain. Coloe Fossae lies squarely within this transition zone. The name Fossae is Latin for ditches or trenches, which is a humble moniker for what is actually a titanic system of grabens. These are blocks of crust that have dropped down between parallel faults, created when the Martian crust was stretched and pulled apart. Billions of years ago, likely driven by the massive volcanic uplift of the nearby Tharsis or Elysium regions, the crust here was put under immense tension. It eventually cracked. Enormous blocks of rock, some kilometers wide and hundreds of kilometers long, slumped downward, creating steep-walled valleys with flat floors. These tectonic scars provided the perfect topography for the next act in the Martian drama, which was the invasion of the ice. Unlike a river valley carved by erosion, the troughs of Coloe Fossae were born of violence. They are deep, box-shaped canyons with walls rising 3,000 meters above the floor, heights that rival the terrestrial Alps. But for eons, these canyons did not remain empty. They became the catchments for snow and ice during the planet's wildest climatic swings. Now, this brings us to the engine of the Martian ice ages. On Earth, we associate glaciers with the poles or high mountain peaks. Finding evidence of massive glaciation in the mid-latitudes of Mars, roughly around 30 to 50 degrees latitude, seems counterintuitive. To understand why Coloe Fossae became a glacial powerhouse, we must look at the sky. The primary driver of Martian ice ages is obliquity, or axial tilt. Earth's tilt is stabilized by our relatively large moon, keeping us at a steady 23.5 degrees. This stability gives us predictable seasons and keeps our ice locked safely at the poles. Mars has no such stabilizer. Its two tiny moons, Phobos and Deimos, are gravitationally insignificant. As a result, Mars wobbles like a dying top. Over cycles lasting hundreds of thousands to millions of years, the red planet's tilt can swing wildly, from a shallow 10 degrees to an extreme 45 degrees or more. When Mars tilts heavily, in periods of high obliquity, the poles point more directly at the Sun. The polar ice caps, composed of water ice and carbon dioxide, become unstable. They sublime, turning directly from solid to gas, thickening the atmosphere with water vapor. Global atmospheric circulation then transports this moisture toward the equator. But it does not rain, it snows. Massive amounts of snow precipitate in the mid-latitudes, accumulating on the windward slopes of the fretted terrain. Over centuries, this snow compacts into ice, growing hundreds of meters thick. This is the Ice Age engine. It effectively teleports the polar caps to the mid-latitudes. Coloe Fossae, with its deep shadowed tectonic troughs, became a perfect trap for this migrating ice. The glaciers that formed here were not small mountain streams. They were massive, sluggish rivers of ice that filled the valleys to the brim. Although the ice is largely gone from the surface today, or hidden beneath thick blankets of dust, it left behind fingerprints that are unmistakable to the trained eye of a planetary geologist. The European Space Agency's Mars Express Orbiter and NASA's Mars Reconnaissance Orbiter have revealed these features in breathtaking detail. The most striking feature of Coloe Fossae is the texture of the valley floors. They are not flat sediments like a dried lake bed. Instead, they are marked by complex patterns of ridges and grooves that run parallel to the valley walls. This is known as lineated valley fill. It looks strikingly like a flowing river that has been petrified. These lines are flow fronts, the physical record of ice and debris moving downhill. As the glaciers flowed, they carried massive amounts of rock fall from the steep canyon walls. When the ice retreated or sublimated, this rocky debris settled, preserving the flow patterns of the ice that once carried it. Furthermore, at the base of the mesas and cliffs in Coloe Fossae, we see bulging convex mounds that fan out onto the plains. These are lobate debris aprons. They look like dollops of viscous batter poured onto a table. Radar data from the Charade instrument on the Mars Reconnaissance Orbiter has penetrated these aprons, revealing a stunning secret. They are not solid rock. They are nearly pure water ice, covered by a thin veneer of dust and rock, perhaps only a few meters thick. This debris layer acts as a thermal blanket, insulating the ancient ice core from the sun and preventing it from sublimating away into the thin Martian atmosphere. Another fascinating signature is concentric crater fill. Impact craters within the Coloe Fossae region show a bizarre anomaly. They are not bowl-shaped depressions. They are filled to the brim with material that shows concentric rings, like the ripples in a pond frozen in stone. This occurs when ice and debris accumulate inside the crater bowl. As the material flows inward toward the center of the crater, the compression creates these concentric ridges. It is a bullseye marker of glacial activity. When we zoom in even closer with the high-rise camera, which can see features as small as a coffee table, the surface of the glacial deposits in Coloe Fossae reveals a texture that is both fascinating and slightly repelling. It is a maze of twisted ridges and pits that looks uncannily like the surface of a human brain. This brain terrain is the result of the slow death of a glacier. Mars is a dry, low-pressure environment. Ice there does not melt, it sublimes. The process begins when thermal stress creates tiny cracks in the debris-covered ice. These cracks expose the pure ice underneath to the atmosphere. The exposed ice then turns to vapor, deepening the crack into a trough. The dust and debris from the sublimating ice remain, piling up on the ridges. This creates a feedback loop where the ridges become insulated by the thick dust, protecting the ice beneath them, while the troughs continue to deepen as the exposed ice vaporizes. Over millions of years, this differential sublimation sculpts the landscape into the wandering, organic maze of ridges we see today. It is a texture of decay, a visual representation of the planet slowly losing its water to the sky. Why does all of this matter? It matters because Coloe Fossae challenges the Noachian bias. For decades, scientists focused on the Noachian period, over 3.7 billion years ago, as the only time Mars was interesting, wet, warm, and potentially habitable. But the glaciers of Coloe Fossae are much younger. They are Amazonian in age, likely active between 100 million and perhaps as recently as 10 million years ago. Some models suggest that during the last extreme high obliquity period, just 5 to 10 million years ago, fresh ice may have been deposited here. This means that liquid water, albeit in thin films or transient melt pockets, could have existed on Mars relatively recently. The pressure at the base of a 2-kilometer thick glacier can lower the melting point of water, potentially creating subglacial lakes or streams even in a freezing climate. If life ever evolved on Mars, it didn't necessarily have to die out billions of years ago. It could have followed the water, retreating into the cryosphere, hibernating in the ice-protected pockets of places like Coloe Fossae. Looking forward, Coloe Fossae represents one of the most strategic locations in the solar system. As humanity eyes the red planet not just for visitation but for habitation, the mantra is, follow the water. Recent studies estimate that the mid-latitude glaciers of Mars, including those in Coloe Fossae, contain over 150 billion cubic meters of ice. To put that in perspective, if melted, this ice could cover the entire surface of Mars in a global ocean 1.1 meters deep. For future astronauts, this is gold. This is the concept of in-situ resource utilization. Water is heavy and impossible to transport in large quantities from Earth. Finding nearly pure water ice protected by a thin layer of loose rock at a manageable latitude, around 40 degrees north, is the holy grail of site selection. This water can be split into hydrogen and oxygen to make rocket propellant for the return journey. It provides oxygen for breathing and water for drinking and farming. It also serves as radiation shielding. Water is an excellent shield against cosmic radiation. Habitats could be buried inside the glaciers or covered with icecrete. Coloe Fossae offers a unique sweet spot. It is close enough to the equator to have reasonable solar power potential, unlike the dark poles, but high enough in latitude to host massive water reserves. The steep canyon walls also provide natural geological cross-sections, allowing geologists to study billions of years of crustal history without digging. To visualize Coloe Fossae, we can look to Earth. The closest analog is not the famous white sheets of Greenland, but the McMurdo dry valleys of Antarctica. In the dry valleys, glaciers flow slowly through a hyper-arid freezing desert. They are often covered in rockfalls and debris, creating rock glaciers that look like piles of rubble but move like fluids. The pitted terrain seen in Antarctica, where sublimation shapes the ice, is a close cousin to the brain terrain of Mars. However, the scale differs. The glaciers of Coloe Fossae were tectonic. They filled canyons wider than the Grand Canyon and deeper than the Rockies. The silence there today is deceptive. It masks a history of immense crushing power. In conclusion, Coloe Fossae is a testament to the resilience of planetary processes. It is a landscape born of tectonic trauma, bandaged by ice and scarred by the wind. It tells us that Mars is not a dead world, but a sleeping one, a planet that oscillates between dry desolation and icy activity. As we gaze at the high-resolution images from Mars Express, tracing the swirling lines of the valley fill and the chaotic knots of the brain terrain, we are not just looking at geology. We are looking at a climate record that may hold the key to understanding the stability of terrestrial planets. We are looking at a potential refuge for ancient microbial life. And, perhaps most profoundly, we are looking at a future gas station and watering hole for the first human explorers of the Red Planet. The scars of Coloe Fossae are deep, but they are not wounds. They are reservoirs of history and hope, waiting for us to break the seal. Thank you for listening to Fun Facts Online.